Okay, so this is a slide that I will put in the Padlet, because I know this is quite a nice overview slide of what mechanics looks like across all of year 12 and most of year 13. And this is just an intro that I showed the year 12s, and I think it's quite nice to see like where this topic actually goes, because sometimes people look at mechanics and they think it's this like unending, like huge topic, and they can't really place the topics where they actually belong. And really mechanics is actually just this slide that we've got here. So I'm not going to talk through this whole thing in detail, but it's something that you'll probably want to have a look at when you go through the notes and stuff afterwards. But this will be on the Padlet. I haven't printed it for you, I'm sorry. So one of the things that we're going to be looking at, and force is actually where we begin in year 13, is we're going to be thinking about how forces interact with different bodies, different particles. And it says here that you will encounter force diagrams. This considers the forces acting at a particular point. Some forces that you might be considering, so you've got your object, you might have weight, reaction force, friction, string, tensions, all of that kind of stuff. And things that we will look at within a force topic. It says forces can be considered as vectors, so you're going to see how that's going to connect together to some of the things we've been doing in pure maths with vectors. We've talked about the magnitude of a force vector, gives the size of the force. We've already spoken about that before. And it says we often consider forces in a particular direction. So if the object above here was stationary, we would say that the forces going to the left would be equal to the forces going to the right, the forces down would be equal to the forces up for things that are not moving. And sometimes we need to consider forces of multiple different points if objects are connected. And this is your kind of pulley sorts of questions. We extend those ideas a bit more in year 13 where we have things connected, but that's our idea of what we have with forces. The other area of stuff that we study in mechanics is motion. And actually, in year 12, you would have looked at these two kinds of graphs, your displacement time graphs. But really, the main focus will have been on the velocity time graph, where the area underneath was the distance and the gradient was the acceleration. Whenever you are asked to draw a velocity time graph, you should always be trying to find the area underneath it if they ask you about the distance. Within this topic, which is about constant acceleration and how things are moving, you had your Suvat formulae. Remember, that only works for constant acceleration. And these Suvat formulae that we have here can be applied to these kinds of situations that we have with anything with constant acceleration. This tiny little bit at the bottom here was when we had variable accelerations. This is kind of like one of the other topics you'll have come across in year 12, where it says that acceleration is not constant. We can specify that the displacement, velocity, or acceleration as functions of time. And that's remembering where you can differentiate or integrate to find out those different things that we would have. Quick way of remembering that as a bit of a recap, if it's a speed velocity time graph and the area underneath is the distance, we know that area is to do with integrating. So if you integrate velocity, you should get what the distance is. And once you know you integrate to get distance, all the other things kind of fit in. So these two topics that we've got with forces and motion, the thing that bridges them together is F equals ma, which is Newton's second law. So you'll see that F, which represents the resultant force, will connect us to this world over here of acceleration and motion through the A part of the formula. So these two things are connected by this formula, and that's when you'll sometimes find like a Suvat kind of question popping up in a question that seems to do with forces as well. Everything that we will look at in year 13 builds on these ideas that we have here, starting with the idea of forces that are acting at angles. So we're going to begin by returning to this topic, then we'll be returning to this topic. Apart from there will be some angles included in that. And then we begin adding in some new things like friction. We start thinking about how do we actually calculate what friction is. We then come back to some of these things with Suvat formulae, and instead of just having things moving, going up and down, we start considering things like more real life, having a tennis ball and throwing it at an angle. Okay, that's one of the things we look at. And it all kind of fits within this scheme of stuff that we have. What do you think might be different about this area that we've got down here for the for the variable acceleration? What do you think might be different in year 13 for that? We won't look at any acceleration time because we're talking about the variable acceleration stuff. What do you think might be different about the types of functions we might come across? So at the moment, these are just polynomials. You'll have only done differentiating and integrating with them. What we'll do in year 13 is the functions may be trigonometry, They may be exponential functions. So all the stuff that we do in pure maths to do with differentiation and integration can find its way into mechanics as well. Vectors kind of fits across this whole thing. Vectors is almost like the different language that you can sometimes talk about with mechanics. You can do some of these with vectors, we'll look at that eventually, and forces can also be talked about as vectors as well. Okay, I will also include in the Padlet notes is some stuff to do with modelling assumptions, because this is something that you should have had a look at in year 12, but from my experience with the other group, they didn't necessarily have very good explanations of some of these things that we've got here. So this is something that as part of your homework, I want you to read through these slides and then come back with any questions that you have about them. It's just when they say things like the ball is modelled as a particle, like what are some of the assumptions? I've written what some of these assumptions are. The dimensions of the object are negligible. What does that mean? It means that the mass of the object is concentrated at a single point. Rotational forces or air resistance can be ignored. So that's if something says it's modelled as a particle and it says, what does that mean? You can say we've ignored air resistance, for example, okay? So this slide has got some of those extra bits that you might want to know about. And then I've also got this slide, which I took from the textbook, that these are some common words that they might use about in these kinds of questions. They tell you what they mean, and then they tell you what we've assumed about the model that we've got there. I'm not going to read through all of those, but as part of your homework, you'll have to read through those off the Padlet to just get yourself familiar with some of that language that we have there, because there's always those 1 or 2 mark questions where it asks you about the modelling assumptions. And I realise you probably haven't been shown those in much detail before. So we'll start the year off with that and then try and use as much of that as possible throughout the topic. Okay, so what we're actually going to begin with is think about what we'll do in this topic that we have right now, okay? We're going to be looking at within forces. We're going to be looking at forces that are acting at angles, which means we can then look at things that are moving down slopes that are on angles as well, rather than just things that are moving on tables. We will then be thinking about friction as well. This is quite a big topic, but it's all that forces part that we've got. We'll then be trying to find unknown forces when things are in equilibrium and not moving. We'll be looking at static problems, which again is just the same kind of maths, but it's just things that are not moving. We then look at objects which are moving on planes. This is sometimes a topic that we call dynamics. Dynamics means things are moving. Statics means things are not moving. And then last of all, we'll look at connected particles, which are also on angled things as well. So it's kind of revisiting everything that you've done previously in year 12, but we just add in some new details. And the good thing about doing that is by looking at these things, we're revising everything that we did in year 12, or, if I'm not going to use the word revising, relearning and understanding things that maybe you didn't understand so much in year 12. So you must make sure if there are things that I talk about here and you think, oh my God, like everyone in the class understands this, but I don't understand this, you must say something, because I bet everybody in the class doesn't understand it, and it's so useful for people to hear those things again, okay? So, again, I know there's a lot of me having to explain some of this stuff in here. I have made a little sort of like a short document that's got some of the essentials, just in case there are some things from year 12 that you've forgotten about, or that you heard about and you didn't really understand why they were true. So if there's anything in here and you're like, oh my gosh, this is so boring, just bear with me for a bit, okay? So a few very basic things. Weight is mass times g. People often get mass and weight confused with each other. Mass is just how much stuff there is. Weight is the force. And it says g is the acceleration due to gravity. We take it as 9.8 meters per second squared. You may also see that w equals mg. This is something that's painfully obvious, but I've seen these diagrams drawn wrong before. Weight will always act vertically downwards. Like in this thing that we've got here, the weight is going downwards. Sometimes I see people drawing weight like that, but weight does not go any other direction other than just vertically downwards. Okay, this also is some quite obvious stuff, but we're going to talk about normal reaction. It says the normal reaction, which is sometimes called the contact force, is the force which acts on a box or particle from the surface that it is on. It's called the normal reaction because it acts normal or perpendicular to the surface, okay? So you'll see in these two diagrams we've got here, the normal reaction is perpendicular to the plane. the normal reaction is perpendicular to the inclined plane in that one that we've got there. Too many people I've seen in the past on this kind of one would be like, oh, well, the normal reaction goes upwards. The normal reaction is normal to the thing that it is on. It is called a normal reaction because it has reacted to the forces in the opposing direction. For example, when you are sat on a chair right now, your weight is acting down, but the chair, which is the surface, has a reaction force upwards which stops you falling to the floor. This is the normal reaction, and we use the letter R for the normal reaction. Sometimes you might see the letter N as well. So just feel that force on your backside now. That is actually pushing you upwards, but what you feel is that force pushing you upwards. Really, it's the reaction of your weight against the chair. I feel it on my feet now. When you go in a lift, you feel that you're heavier. You're not actually heavier, but the normal reaction when you go up in a lift, you know, and it kind of makes your knees feel like they're bending a bit more. That's because the normal reaction from the floor is higher, pushing you up. So I've just said on these two diagrams, note that the weight acts vertically downwards, but the normal reaction is perpendicular to the slope. Obviously here the weight is 5g and the weight here is 2g. You take the mass and you multiply it by g, which is 9.8. Some very basic stuff from year 12. Apologies if this is very, very boring. It probably is. But Newton's first law says that an object will remain at rest or will continue to move with constant velocity unless acted upon by an external force. Essentially, this means that something will not move, or it will move with no acceleration if there is no overall resultant force. It means that all the forces are balanced, and we call this equilibrium. Obviously, the word equal is part of that word equilibrium. So for this example that I've got here, I've said, given that this particle is at rest, work out the value of P and the value of R. So I've said clearly R is equal to 2g. Too many people in the past will say, oh, well, R is always equal to the weight. R is not always equal to the weight. In this particular situation it is, because there's only one force up and one force down. Clearly P is equal to 10 because it's in equilibrium. Forces left equal forces right, forces up equal forces down. If it didn't say that the particle is at rest, if it said that the particle is moving at constant velocity, would it still be in equilibrium? It would still be in equilibrium. Look what it says. An object will remain at rest or will continue to move with constant velocity unless acted upon by an external force. So if it's moving with constant velocity, it has no acceleration. No acceleration means constant velocity, which means equilibrium. So there is only going to be imbalanced forces if something is accelerating and getting faster and faster and faster. You can kind of think about that when you're cycling a bike. If you want the bike to get faster and faster, you have to put in lots of work to be faster than the wind pushing against you. If you want to keep at a steady speed, your cycling energy that you put in, your force you need to put in, needs to be equal to the wind that you're cycling against. Okay, so you still need to put a force to keep those things balanced. And if you're at rest on a bike, obviously your forces are balanced because you're not doing any cycling at all anyway. Okay, so we're actually now going to get into some of the stuff that, again, if you do physics, I'm sure this is very familiar, but I just wanted to now actually dive in with a bit of maths that we've got here. So we know from vectors that you can split something up into two component pieces, okay? So this 6 newtons that we've got here, for example, if I was going to say that this is actually a vector, we're going to think about how we can split this force up into two different forces. If I was going to change it into a long vector, let's do this in the black colour, I could say there's that arrow and there's that arrow. Now we know with vectors, this vector plus this vector is equal to this vector here. That's from our idea when we have things like this, where you have vector A, vector B, that one would be A plus B. Same thing, okay? So we're allowed to split these things up. And these triangles will obey like Pythagoras and SOHCAHTOA. So I'm just going to do this one really quickly. This one that we have running along the bottom here, let's just draw that triangle out separately for a second. This is 6. If I was going to try and find this one that's running along the bottom, what's the trig ratio that relates these things together? Yeah, it's 6, but what's the trig ratio that relates them is cosine, because cosine theta is the adjacent over the hypotenuse. So when you multiply up, you get 6 cosine theta is x. So this one running along the bottom is 6 cos theta. What would be the one that's running up along the side? It would be the sine theta, because this bit is involving the opposite and the hypotenuse. So when you multiply up by the hypotenuse, you come up with 6 sine theta that you have. Can you notice how, as I've drawn these arrows on, as I've drawn these lines on, I've drawn them as arrows, and I've drawn the directions that they're going in. So this overall force, which is pulling up diagonally at 6 newtons, it's actually a combination of a force pulling it to the right and a force pulling it to the up, pulling it upwards. What can you say about 6 cos theta? Is it the same as 6, bigger than 6, smaller than 6? Has to be smaller than 6. And this one also has to be smaller than 6 as well, which is good. Kind of makes sense if you've got 2 forces that you've split to one overall force. They've both got to be smaller than 6. And this also obeys the idea of Pythagoras, because if you square this one and square this one, add them and square root it, you'll get 6 as well. So what do we think this one here gets split into? What should this one running along the top be? Yeah, it's 10 cos theta. How did you spot that so quickly, Hamza? Yeah, but what do you look for? That's what I'm wanting you to explain.
When we're doing physics, right, is think about that line, and if you're going across the angle, it's cos, because across has cos in it, and then if it's the other way, it's sine.
Okay. So, no, I get what you're saying. But the way we think about this, so the reason we know that cos is the one that belongs next to the angle, because cos is with adjacent, right? So, ka, toa. Cos is adjacent, sine is with opposite. Cos goes with adjacent, and sine goes with opposite. So if that one is 10 cos theta, this one would obviously have to be 10 sine theta. Notice when I do the arrows, I'm starting from where the force begins, and I'm ending up where it does up here. So this one running along the bottom here would be what, Sarah? What would this one be? 12 cos theta, and then this one is going upwards. I know it's going upwards because it's starting here. It's an across and an up. 12 sine theta. So more generally, that I've got written on for this one, F can be resolved into 2 forces, which is F cos theta and F sine theta, identified by whether it's adjacent to the angle or opposite the angle, and I've written that down here. If F is the magnitude or the hypotenuse, use F cos theta for the side adjacent to the angle and F sine theta for the side opposite it. Now, what's the point? What's the point of taking a force and splitting it up into 2 things?
So it would always be cos horizontal?
No. No, because if I did one that looked like this, that's a force going over there. Just depends where the angle is that you're measuring. Okay? So that would be the 8 cos theta, and that would be the 8 sine theta. It's all relative to the angle. So what's the point? Why, physicists, seeing as I can see you all looking around being like, oh yeah, this is so easy, what's the point of resolving forces?
So you can find like unknown forces from different things.
Yeah?
So you can find out unknown forces.
What's special about forces that are perpendicular to each other?
They don't interact.
They don't interact with each other, and it's also written in this box up here, so well done, Hamza. If you think about it, perpendicular forces can't interact with each other, okay? If you were trying to like move my bottle like up towards the ceiling, but your only power was being able to like move things left and right, you can try all you like, you're never going to be able to make that bottle go up or down unless you push it off the edge of the table. But you know what I mean, right? Left and right can't have anything to do with up and down. Perpendicular cannot interact with each other. And you actually see that with a lot of things in engineering and physics. Things that are perpendicular either interact with each other loads or they don't interact with each other at all. Okay, and that's quite a special property about things. And luckily it makes maths become pretty easy, okay? I also said there, they obviously obey SOHCAHTOA and Pythagoras rules. Okay, so statics, you're going to come across this word. When I talk about a problem and I say it's a static situation, we're saying that something is not moving, which means that things are in equilibrium. So I've said this, static means there is no movement. This means there is no acceleration. So we said no acceleration from Newton's first law means it's in equilibrium. All the forces are balanced in any direction at all. Whichever way you resolve them, they have to be balanced. We come across this later on when we study moments, which is about like seesaws and like beams and stuff that will be moving. Those will also, equilibrium means that it's always going to be balanced in any direction that you look at things with. Forces left, forces right are equal, forces up, forces down are equal to each other. Now this is something, again, physicists, you may do this. I don't know how you do this in your class, but we'll have a look at how we do this. So this is a scenario that I've got here. I've got a particle, which is of a negligible mass. I'm not going to say it doesn't have any mass necessarily. And actually this is something which is doesn't really matter, but I'm thinking of this one as like a bird's eye view, like a plan view of this. And I've got some different forces here that I need to resolve, and I need to split these forces up. So, Ahmed, what would this force running along here be? What would, if I'm looking at this force, which is P, and I'm going to split it up into two forces, what would this one be named here? Wouldn't be an X1. Anyone, what should this one be? Okay, so the hypotenuse of it is P, and it's adjacent to the 30 degrees. So this one would be split as a P cos 30. Okay? Is this, Abraham, is this going to the right or going to the left?
Right.
Why did you say that like kind of questioningly? You're not sure? Is it just a guess? No? No, just answer the question honestly. And then this one is going up, because we can see the way it's following. This one would be P sine 30, okay? Sarah, what would this one running here be? 4 cos 45. Is it going to the left or the right? So the force is overall is going like this. So what do you think that's a combination of? What kind of, if you were to describe that direction, but only using up, down, left, and right? How would we describe that? Yeah, up and left. This force is going up and left. So this must be a left, and this must be an up. And you can just see it follows the same pathway. That one must be 4 sine 45. And then Q, what do I need to do to Q? Nothing. It's already going in a perpendicular direction, okay? Now this is something I would highly recommend you do because I know where this course goes. Physicists, I also know it goes more complex than what you do in physics. So you're going to look at me now and be like, I don't need to do that. But you need to trust me because I'm training you to do much more complicated things in the future. It does become more complicated than what you do in physics because we go a lot deeper. So what I would recommend doing after you've drawn this is to redraw the diagram and to remove the diagonal forces and just to replace it with the horizontal forces that we've got. So I've still got a force of Q newtons that's going downwards. Shahid, what do I have that's going to the right? Do I have any forces going to the right?
Yeah.
What do I have?
P cos 30.
Do I have anything else going to the right? Nope. Okay, as soon as I've done P cos 30, my advice is then to add in its friend, P sine 30, which I know is going up because once I've got those in, they're done. Notice how I've put those two in. I don't now put P in because I've already put P. I've taken P and split it into two forces. I won't put P in again. I've already put it in by breaking it down into the two pieces that are there. Then I've got, also going upwards, 4 sine 45. Whoops, got to be careful about squeezing it in. And to the left, I have 4 cos 45, okay? This second diagram, I believe it is far easier to look at because you don't have this kind of mess of all of these different things that are happening at the same time. Also, you're going to have way more complicated ones coming up, okay? So what do we do to find out the size of P and Q? Huh? You have a question, yeah? Oh, you're going to answer the question? Yeah, go for it.
If it's in equilibrium,
Yep.
4 cos 45 is equal to P cos 30.
Yeah, good. I'm going to write this letter at the beginning and I'm going to do these arrows This R means to resolve. All the word resolve means is to kind of like compare the forces, and this means which direction I'm looking at it in. You don't have to do this, but it's very good communication, and it means that you make whoever's looking at your work understand it and give you the marks you actually deserve, okay? If an examiner's marking 1,000 exam papers and they can't see what they're looking for within 15 seconds, you might not get the mark, okay? You might get it if you remark it, but by then your uni place might have gone. So make what you're doing as clear as possible. So when we go left and right, Hamza just said that these two forces must be equal to each other. P cos 30 must be equal to 4 cos 45. Can I just quickly ask you, why did you do left and right and not up and down first?
Because we already have numbers for 4 cos 45, we can get looking.
Yeah, we can actually find out what P is. What would be the bad idea of doing up and down?
Because we still have 2 unknowns.
You still have 2 unknowns, okay? You've got P and you've got Q. So this cos 30 and 4 cos 45 are just numbers. So P is 4 cos 45 divided by cos 30. Make sure you're in degrees mode, because obviously we're now working in degrees. So 4 cos 45 divided by cos 30. And we get 3.27 newtons to 3 significant figures. The accurate version, though, is 4 root 6 over 3, because you might use that later on in the question. Okay, and then when we resolve up and down, Hassan, what do we get when we resolve up and down? Okay, so when you look at this diagram, all you're going to tell me is the up forces equal the down forces. That's it. So what are the up forces?
So 4 sine 45
Yep.
plus?
Yep. Plus, because it's the overall forces. Yep. Plus P sine 30 equals to Q. Okay, so if I want to find out what Q is, I can now take these values that I've got here and just substitute everything in and calculate it. So let's just take whatever I've got on my calculator still and just work out this that I've got here. So Q is going to be equal to that times sine 30 plus 4 sine 45, and we should get 4.46 newtons to 3 significant figures. Yes?
Would you also have them if there was more than one force going to the left and right?
Yes, you could have some diagrams where you might have 2 forces going this way, 3 forces going this way, okay? You could definitely have diagrams that look like that. One thing to notice just before we move on here, I said this before, you've got those pair, which are like a pair. You have to have both of them. You can't just have one of them. If you've got one of them missing, you're going to ruin the rest of your question. So that diagram at the beginning is really important. That's also a pair as well. Q doesn't have a pair. Why didn't Q have a pair? It's already resolved, okay? It's already resolved, and it's fine the way that it is, okay? So I made a printing error on the next page, so you're going to need to adjust the example that I've got on the next page for me, okay?
Sir,
Yes.
you know when you say the change in KD, would you put initial left and final on the right of the equation? Because the final was 0, but I thought the initial was 0, I'm confused.
The change in, this is something completely separate, by the way. The change in KE will be, that's how much energy is being spent on something, the change in KE. So you think about where that goes, okay? Okay, so what you need to change about the example on this page is, I foolishly called it R, and people kept thinking I was talking about a normal reaction, and this one has to be 16 newtons. I think that's the only change I made. I think it's still Q and 12. So if you can just change those things that you've got there. What I'm going to do is I'm going to just give you, after you've changed that, I just want you to draw the angles that you think that there should be on this diagram. And then I want you to draw the second diagram, and then we'll compare it and see how we've done on there, okay? So you're going to draw some of the angles in. You may like to use 2 colours for this. If you want to use colours in a mechanics exam, that's fine. and then we're going to draw the second diagram. Even if you do physics, I want to see the second diagram, please, okay?
Sorry, what's the second diagram again?
There's this is another bird's eye view. Okay, this is another bird's eye view. This is not something that's got weight, okay? This is just, I've told you everything that's in the diagram. Just have a look what's on it.
It's an equilibrium.
Yeah, we're still in equilibrium here. Haven't said anything different.
It's annoying. Oh, don't worry. I mean, considering anyways. So that's where. Just do half MV squared. Yeah. Don't worry. When I get to it, it's. Okay. Don't worry, man. Just give me time. That's all I need. Just like I did in my system.
Make sure when you put them on your second diagram that you have pairs, okay? Pairs of everything. There's no weight. This is a bird's eye view.
Also, what is proper stringing. Yeah, proper. Like he touched it. It's a wonderful. He jumped from a building.
Okay.
I would take that from me. I'll leave you to keep it just for now. I will take that.
Okay, just 30 seconds more.
Saying I'll just be laughing.
I'm going to ask you to help me with a couple of these, okay? I'll ask you to help me with a couple of them, okay? Okay, Tashina, what did you split the 16 up into? What was going along the bottom?
16
To the left? Okay, so we have 16 cos 40. Hamza, not now, please. And then going up was your... Okay, what about the Q force that you had running to the right?
Q cos 30.
Okay. And then going up was obviously then Q sine 30. Did you do an extra arrow going to the right for the 12 as well? Yeah, because there is another force that's in there. So I'm not really sure how I'll fit this in. That's a 12 cos 50. 12 cos 50, and then coming down is the 12 sine 50. Nothing needs to be done to the P force that we've got there. So it's pretty messy, this diagram, which is why I highly, highly recommend doing a second diagram, okay? What forces do you have that are going in the upward direction? Ahmed, what do you have going in the upward direction? 16 sine 40. Q sine 30. Anything else? And P. Okay, I don't really know how I can fit this in my diagram, but it could come all the way up here and P. Sometimes you can write those all things being added together as well. What forces do you have to the right, Amara?
Q cos 30 and 12 cos 50.
Q cos 30 and 12 cos 50. In the downwards direction, what do I have, Habib? 12 sine 50. I didn't write that out properly. It's 12 sine 50. Anything else? No, and to the left? 16 cos 40. Okay, once we've made the effort of doing this diagram, I mean, mine's not particularly neat, but once you've got to that stage, it should all work out fine, okay? We said that we should do some resolving. Are we going to do up and down or left and right? I think left and right. I think left and right is going to be the best way to do this one because we've only got one unknown. So we've got 16 cos 40 must be equal to Q cos 30 plus 12 cos 50. Now it's so easy. We've got three different angles here. It's so easy to start writing the wrong angle. So just be really careful when you write this into your calculator. So it's 16 cos 40 minus 12 cos 50 divided by cos 30. And that will tell us what the force of Q is. So let's get that done nice and quick. 16 cos 40 minus 12 cos 50 divided by cos 30. I think it should be 5.2461, blah, 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 which is 5.25 newtons to 3 significant figures. Then I'm going to resolve in the up and down direction, and I wonder if we're going to notice something that will happen here, okay? So in the up and down direction, I've got these up forces equal this down force that I've got here, okay? So I have P plus 16 sine 40 plus Q sine 30 equals 12 sine 50. So P is equal to 12 sine 50 minus 16 sine 40 minus Q sine 30. Hopefully you've still got Q on your calculator screen as the answer, so you can just use that answer button when you type it in. Anyone think they know what's going to happen when we press equals for this? Anyone got any predictions? Pardon? Yeah, it's going to be a negative, and I'm going to explain why that's there. There usually won't be one, but I've put this in because I just want to show you what might happen if you were to draw a diagram for something in the long future and you get a negative. What does that mean? Okay, so let's just quickly work out. We've got 12 sine 50 minus 16 sine 40 minus answer Q sine 30. And I've got the answer minus 3.715, blah, 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 which is minus 3.72 newtons. Shouldn't really have a negative. What do you think that negative might actually mean about our diagram? Yeah, it's a direction. I put this in because I want you to think. Sometimes you might think something is in a particular direction and you might do a calculation and you get a negative. That's not telling you that it's a negative force. That's actually telling you that the force that we had here isn't actually acting in that direction that we believed it to be acting in. So really what we should say here is it is 3.72 newtons downwards. Okay, the diagram was actually wrong to begin with. P originally was drawn incorrectly. Now, obviously, I gave you the question, so it's very odd for me to give you a question that is wrong. But there will be some scenarios where you draw the diagram and you don't know which direction whatever forces you're trying to find out is, and you think, okay, well, I think it might be up. It's not up. Ends out, you get negative, and it turns out being down. You're not going to get something that's up and it turns out to be left. Okay, it's always going to be up or down or left and right. But if you ever get a negative answer, it does have a meaning. It doesn't mean, uh-oh, you're wrong, or, oh, let's just ignore the negative sign. It has a significance in mechanics. That's why I wanted to include that question we've got. Okay, so time for you to do some practice. I have reordered the questions, okay? So I've just said here, I want you to try this one last, just because there's a little bit of extra maths that needs to happen there. And yeah, try that one last. There are the answers down here as well. Before you work out P and Q, please just listen before you start doing any of this. I want you to draw the second diagram for all of them, even including this one. Then I want you to do the mathsy bit. And when I mean the mathsy bit, I mean like this bit. So I want every question to have this bit first. Then I want you to work out what P and Q are for those questions. Probably easy if you do them. Pardon? B. Do this one last, just because it's the maths of that. There's a little twist that we'll talk about at the end. Okay? So draw all those diagrams, and I'll come around and have a look at those and see how they go.